Hello everyone. In this video we are going to talk about elementary matrices and inverses. So we're going to start by talking about elementary matrices. So an elementary matrix is a matrix that differs from the identity by exactly one row operation. And it turns out that these will correspond to, when you multiply by them, actually performing row operations on matrices. But we'll get to that shortly. So first, what do we mean? Well, we have three types of row operations, right? So one, we can switch rows. So an example, right, you would start with, let's just do 3 by 3 examples for each of these. So you could start with the identity, and then an elementary matrix would be, let's flip the first and third rows, right? So you do that, and we would get 0, 0, 1, 0, 1, 0, 1, 0, 0. So this would be an elementary matrix of the first type. You can, of course, scale a row. So again, right, start with the identity, and then here we can scale any row. So let's just scale the middle one. Let's multiply it by some scalar c. And then we would get 1, 0, 0, 0, c, 0, 0, 0, 1. And finally, we can add a multiple of a row to another row. And for this, again, we'll see something similar. So let's add 2 times the first row to the third row, right? So in that case, we're going to end up with basically the identity back, right? Our first 2 rows are unchanged, and then we add 2 down here. And so you'll see that basically the first one is just 2 rows have been switched from the identity. Right here, it looks like all ones along the diagonal except for one thing has been scaled. And then the last one is all ones along the diagonal, and then somewhere we have added a multiple of a row by putting some constant in one of these kind of lower triangle spots. Okay, so now let's look at what happens when we multiply on the left by these elementary matrices. So I say on the left, I'll show you what happens on the right here in a second, but basically on the left is going to correspond to row operations, and right will be column operations, which of course we don't really do as much because we do row reduction. So what happens here? Well, we should just check out the multiplication. So in this case, right, I've switched rows 1 and 3, and so when I multiply here, I get, 0 times the first thing in a column, 0 times the second thing, and then this 1 picks up exactly the third thing in each column, right, which is exactly the third row. So this is just going to copy my third row into the first row. My 0, 1, 0, that's just picking up the 4, 3, 2, and 1. Right, so that stays the same. And then my 1, 0, 0 is exactly picking up my first entry in each column, and thus copying over the first row. So what have I done? I've done exactly switching rows 1 and 3 by multiplying by the matrix where I switched rows 1 and 3 in the identity. Okay, that's not by accident. So that will always be the case, and I'll talk about the general thing here in a moment. So if I have a 3 in here, so as we just saw, right, so the 1, 0, 0, this will copy the first row, so that's going to stay the same. The 0, 0, 1 will copy the last row. What happens to the middle row here? Well, I have 0 times the first entry, 3 times the second, 0 times the third, and that's going to happen throughout, right? And so this will be 12, 9, 6, 3. All I've done is this is times 3. And then for the last one, so I added 2 times row 1 to row 3 here. And again, the 1, 0, 0 is going to copy. 0, 1, 0 is going to copy. What happens for the last thing? So we have 2 times 1 plus 2, right? Then we have 2 times 2 minus 2. We have 2 times 3, right? And so on. And so what you're going to end up getting, so I'll just write out the simplified, right? So 2 times 1 plus 2 is 4, 2 times 2 minus 2 is 2, 2 times 3 is 6 plus 2 is 8, and 2 times 4 is 8, minus 2 is 6. And so this is exactly plus 2 times row 1. So basically, whatever you do to the identity matrix, when you multiply it on the left by another thing, that's actually what you're doing to that thing. So this is another reason you can think of them as elementary matrices. They are actually performing row operations, our elementary row operations, when you multiply on the left by them. So a very natural question would be like, what happens if I multiply on the right? So this is obviously an elementary matrix, right? I have switched my first and second rows of the identity. But what happens when I multiply here? So I do 2 times 0 plus 3, so this is 3. And then this is 2, okay? 5 times 0 plus 6, and then 5. Okay, so what has happened? Well, if you see here, we have actually switched the columns. And the reason is basically when you're multiplying on the right, like this 1 here, for instance, right? Every time a row is multiplied by this first column, you're picking up the second thing in that row, right? You're picking up the 3 and the 6, and so you're copying over the second column by putting a 1 in that second row. And so this is just the difference between left and right. So here you're copying columns with the 1s as opposed to copying rows. Okay, so again, we don't really do column reduction, so we will usually just be thinking of multiplying on the left. And here are the general rules. So here's the first one, right? To switch rows, I and j, you multiply by the identity matrix on the left, but with its rows I and j switched, so it looks something like this. So here you can think of all the blank entries as zeros, so it's just 1s along the diagonals, 0s everywhere else, except for you've switched the I and j rows so that those are not 1 on the diagonal, but they're in the kind of opposite spots. The second one is to scale row I by c, and in here, right, we multiply by the identity matrix, but in row I, column I, we have a c in place of the 1. And the last one is we add c times row I to row j. So we're affecting row j. And so basically the thing should occur in row j, and it's just the identity normally, and then we just put this c in column I of row j. So now we're actually ready to talk about inverses. So if we have a multiplicative identity, right, so just think in real numbers, we have 1, right? X times 1 is 1 times x. This is just x, right? And then what is our inverse, right? Because once we have an identity, we can talk about an inverse. Well, this would be 1 over x is x inverse if, of course, x is non-zero. So for matrices, first of all, if you want to be able to multiply on both sides by something to get back to yourself, you've got to be square, right? So we're actually going to restrict, the only time we're going to have an inverse is if we are a square matrix, so same number of rows and columns. And this corresponds to A times, right, the identity matrix is the identity matrix times A is A. So then a natural question would be, do we have a notion of inverse? Do we have a multiplicative inverse? And the answer is sometimes. So similar, right? You needed it to be non-zero there. It's a bit more complicated here, but the answer is sometimes. And we have a nice way of seeing this because of what we just did. So first of all, what would it mean to have an inverse? So it should mean, right, so like x times 1 over x is 1 and vice versa. So we should have A times A inverse is the identity, my version of 1, is also equal to A inverse times A. And so what we're going to focus on here is this. So if I start with A, and then I can multiply by stuff on the left and end up with the identity, I have an inverse. So think about what we have just done before with these elementary matrices. The idea here is to multiply by elementary matrices. These correspond to row operations, right? So we're basically just doing row operations to reduce A which is square, to the identity matrix, right? And so basically we should just have maybe several, but this would work. So let's look at an example of this occurring, okay? So if I have like 1, 2, 1, 1, then I can, if I'm going to row reduce this to the identity, what would I do? So I would first probably just subtract row 1 from row 2, right? I'm going to get to 1, 2, 0, 1. And then I'm almost there. Then I need to subtract 2 times row 2 from row 1. And then I get to the identity, right? So how can I view this? Well, what is the matrix here that does subtracting by row, or subtracting row 1 from row 2? Well, this would be negative 1 here, 1, 1, 0. And this over here, I'm subtracting 2 times row 2 from row 1, so that should be a negative 2 in the second column of the first row. And that's going to be this. But I'm doing them in the opposite order, right? I'm first doing this, then this comes second. And so if I'm thinking about multiplication, this means that if I have 1, negative 2, 0, 1, times 1, negative 1, 0, 1, times the thing I started with, this is going to be the identity, because I performed exactly these 2 row operations, and that should give me 1, 0, 0, 1. So then what's my inverse? If this is A, this is my A inverse. So the 2 things that we really want to conclude from this is, 1, we know when an inverse exists. It's going to exist if A can be reduced via row operations to the identity matrix. And we know how to get the inverse, namely, if we have the row operations in order given by matrices E1, E2 down to EK. These are elementary matrices, right, performing those row operations. Then we want to reverse that order, right, because this says I do E1 first, then I'm going to left multiply again by E2, I'll do that second, and then EK is the last one to do. And so we want the multiplication kind of in this reverse order, and that will give us our inverse. Okay, so here's your one exercise. So I want you to show all the steps. So it's basically going to be finding A inverse here. So I'll spoil things and say it does exist. So you should be able to reduce this to the identity, show all the steps of that row reduction, and I want you to then write down the elementary matrices corresponding to each row operation you did. Given that fact, that means you should really only do one at a time. You shouldn't have any steps where you do 2 row operations simultaneously here, because then that won't be an elementary matrix. That would be like multiplying 2 of them. So make sure you're just doing 1 step at a time. I was able to do this in 4 steps. You might do it a little differently. And then the last step is to find A inverse. So you should, write it as the product of those elementary matrices. Make sure you have it in the order that you are doing them when you're thinking about the multiplication. And then actually compute that product. So I got 4 matrices, multiply those 4 together and see the one matrix that you end up getting. All right, thank you for watching.